Hello, and welcome to Chapter 6, where we're still in the probability distributions. This time we're looking at discrete probability distributions. So, again, you know the drill as we walk through. Let's see what learning objectives we're going to have in this PowerPoint. First off, we're going to identify the characteristics of a probability distribution. Distinguish between discrete and continuous random variables. Compute the mean, variance, and standard deviation of a discrete probability distribution. Explain the assumption of the binomial distribution and apply it to calculate probabilities. And explain the assumptions of the Poisson distribution and apply it to calculate probabilities. Again, lots and lots of fun stuff going on there. Okay. Let's see what we got going. Starting off first, what is a probability distribution? Well, a probability distribution is a listing of all the outcomes of an experiment and the probability associated with each outcome. Our characteristics of a probability distribution that we got is that the probability of a particular outcome is between 0 and 1, inclusively. Is that 1? Looks like I. Looks like I. Aye. Okay, the outcomes are mutual exclusive, and the list of outcomes is exhaustive, so the sum of the probabilities of the outcomes is equal to 1. So their example that they typically use is a drug manufacturer may claim a treatment will cause weight loss for 80% of the population. Yay. The claim could be tested by a consumer protection agency using a sample and statistical interference. Basically, they're going to check to make sure that 80% is accurate. Again, it's a sample population, so it could be, could not be, depending on that situation. What they're trying to do is basically seeing if they can repeat the experiment. So, their distribution example is also a coin toss. So suppose we are interested in the number of heads showing face up when 3 tosses of a coin. Okay. The possible outcomes are 0 heads, 1 head, 2 heads, and 3 heads. And of course, here's their contingency table showing the possible results. So they've done it 8 times. Each time they flip the coin 3 times. So each experiment, basically. Some got heads and some didn't. As we can see, we did have one time where it's all 3 tails. So forth and so on. So all these are possible results. Again, remember when we did the probability and try and find all the outcomes that you can get. Here sometimes it is, and it can get complicated. Alright. Probability distribution tables in the chart of events of 0, 1, 2, and 3 heads. Well, tossing the coin 3 times resulted in 8 different outcomes. The events of 0, 1, 2, and 3 heads are mutually exclusive and exhaustive so that the sum of the probabilities is 1. Okay. Basically, we have seen how many times, number of heads, 0. We only have 1/8. And the only time that we can get 3 heads is 1. So 1/8. To show up only 1 out of the 3, it's 3 out of 8. 2 is 3 out of 8. Again, all add up to 1. We're trying to find all the fun outcomes. Random variables. Randomness. Yes. In any experiment of chance, the outcome occurred randomly, and so are called random variables. Yes. Random variables can be measured with quantitative variables or qualitative variables. That's going to be the fun part. So, examples that they can provide for us is the number of employees absent from a day shift on a Monday. That number can vary. So, it can be 0, 1, 2, 3, so forth and so on. It's a random variable. We do not know this for sure. The grade level of freshman, sophomore, junior, senior of the members of the St. James High School varsity girls basketball team. Grade level is also a random variable, and notice though that this is qualitative variable. It's a qualitative one because it is random. We don't know for certain. It could be all freshmen, it could be all sophomores, it could be junior, sophomore, freshman. We don't know for sure. So again, we're looking at this randomness. It's items that we really don't know for sure. Two types of random variables. One type of random variable is the discrete random. And a discrete random are usually the results of counting. Okay, so it clearly has separated values. Discrete random variables can also assume fractional or decimal values, but the values must be separated by having distance between each value. Okay, so example, tossing a coin 3 times and counting the number of heads. Okay, separate values. So again, we're looking for items to be actually separate in a range. So for example, the Bank of the Carolinas counts the number of credit cards carried by a group of customers. The number of cards carried in the discrete random variable. Number of cards 0, 1, 2, 3, 4 or more. Notice there is separation, 0 and 1. We're not looking at 0, 0.1, 0.2, so forth and so on. We do have separation. This is where we got discrete. And it does show the frequencies. Okay, so 0.03 to 0.10, 0.118, 0.21, and 0.48 of card-carrying people. Again, adding up to 1. They like to do examples. Lots and lots of examples. Now, what does a continuous random variable is? Well, this random variable that may assume an infinite number of values within a given range. They are usually the result of measuring. That's what they always are. So, basically, their random variables are measured with interval or ratio scale, and the likelihood of a continuous random variable can be summarized with a probability distribution. This will be covered in the next chapter. We're going to talk all about continuous with chapter 7. So, yay! Everybody go, yay! Yay! So examples is like the time between flights between Atlanta and LA are 4.67 hours, 5.13 hours, and so on. The annual snowfall in Minneapolis, Minnesota measures in inches. Again, more measurements, continuous. Formula time! So, with the formula stating, it's time to look at mean and variance of a discrete probability distribution. The mean is a typical value, again, used to represent the central location of the data. Little bit of review right there. The mean is also referred to as the expected value. adding on. So, the mean of the probability distribution, there's mu again, will equal the sum of probability of the value x multiplied by the value of x. So, this is going to be fun. Going to use Excel something more. The amount of spread or variation in this data is described by the variance. So, our variance will equal the sum of basically x minus mu squared times the probability of outcome of x. Don't worry, we'll get into how the math works on all this, as we always do. The standard deviation of the probability distribution is the positive square root of the variance. So examples. John Ragsdale sells new cars for Pelican Ford. John usually sells the most cars on a Saturday. He has developed a probability distribution for the number of cars he expects to sell on Saturday. The number of cars sold, 0 to 4. Probability, 0.1 for 0, 0.2 for 1 car, 0.3 for 2, and 0.3 for 3, and maybe 0.1 for 4. Guess that's a really good day if you can sell 4 cars. So, what type of distribution is this? This is a discrete probability distribution. How many cars does John expect to sell on a typical Saturday? Well, again, to find the mean, basically we add it up, we're going to get probably roughly to 2.1. How do we do that? Well, take x times the probability of x to occur, and then we'll go on, add, and divide. Or actually, we're just adding them up. Yeah, so add them up. So again, this is what they really did. Whoops. Alright, so 0.2 plus 0.6 plus 0.9 plus 0.4. So that's where we got our 2.1. Now, so typically he sells about 2.1 cars on a typical Saturday. In other words, over the long run, said 50 Saturdays in a year, he can expect to sell 105 cars. Basically taking our 2.1 times 50 Saturdays, that's how we get to 105. Alright, so what's the variance? Alright, so the same way that we computed before, when we were dealing with variances, we're going to subtract the mean from each value of x. Okay, being that 2.1. All right. So, again, we'll only look at value of x. Then we're going to square that answer. And then from the square, we're going to multiply it by our probability. Okay. Yeah. And then, of course, they're going to add it all up. And that will give us to the 1.29. Okay. And then we find the square root of that, which will give us our standard deviation of 1.136. So again, we're going to go through Excel and showing how it all happens. So again, they took 0.441 plus 0.242 plus 0.03 plus 0.243 plus 3.61. There we go. And then they took the square root. Okay. So yes, we're going to do Excel. All right. Next, binomial probability distributions. Now we already know this is probably going to deal with two possible outcomes. Thus, binomial. Bi always means two. So the binomial distribution is a widely occurring discrete probability distribution. There are going to be 4 requirements for a binomial probability distribution. Again, like we said, there are only 2 possible outcomes, and the outcomes are mutually exclusive, as either a success or a failure. Okay? The number of trials is fixed and known. The probability of a success is the same for each trial. Each trial is independent of any other trial. So, example, a young family has 2 children, both boys. The probability of a third birth being a boy is still 50%. The gender of the third child is independent of the gender of the other 2. We can't really say for sure that she's going to have another boy just because she's had 2 before. It doesn't do anything because, again, like we said, it is independent. We're about to get a lot of fun. So use the number of trials n and the probability of success, pi, to compute binomial properties. Okay. Really, the Greek letter pi is used to denote a binomial probability parameter. The formula to compute binomial probabilities we're going to get to in just a sec, but don't confuse it with the mathematical constant, the 3.14. They're just using it. They're just using the symbol. Okay? So, for a probability experiment, again, an outcome on each trial of an experiment is classified into 1 or 2 mutually exclusive categories, a success or a failure. The random variable in the number of successes in a fixed number of trials. The probability of success is the same for each trial. The trials are independent, meaning that the outcome of one trial does not affect the outcome of any other. Whew. Okay. See, there's our C combination. Alright. So the binomial property formula. Another fun formula that we got. So it reads the number of trials combined with the random variable defined as the number of successes, probability of success of each trial to that random variable, multiplied by 1 minus our probability of success to the number of trials minus the random variable defined. Wow. But NCX pi to the x multiplied by 1 minus pi to the n minus x. Yes. Fun formula. Just be smart. Write down that formula. But dang, that's fun. But C does represent a combination. We calculate combinations in the last chapter. Gave you that homework problem that had the combination. So, in this example, we're going to just insert the value of x that you wish to find, and the value of 10 for n and 0.28 for pi and solve. That's really all we do. So, recently, www.creditcards.com reported that 28% of purchases at coffee shops were made with a debit card for 10 randomly selected purchases at the Starbucks on the corner of 12th Street in Maine. So, what is the probability that no purchases were made with a debit card? X is going to equal 0. Again, that's the number we wish to find. So we're going to take our probability and replace x, which I don't know why they decided to change to r all of a sudden, but that's basically x. Again, they just decided to change it all of a sudden. Don't matter, still x. All right. So we know n is 10, x is going to be 0. So the combination of 10 and 0 is basically going to be 1. 2 pi, which is 0.28, basically the percentage, the rate. 2, 0, that's 1. And 1 minus 0.28, 10 minus 0, which is 10. So however, 1 minus 0.28 to the 10th power gives us 0.0374. And likewise, it's 0.374. We're going to go step by step with one of these. Alright. And the same thing for if 1 happens, which again, 1 is a little bit easier as well. So we get 10, 25, 0.0520, 10 minus 1. And that comes out to 0.1456. I know. Just seems so fun. Alright, so binomial probability distributions. Here's everything. They went ahead and produced the whole chart and came out to where the probability is a little bit higher with 3. You can see it's actually more positive skewed as we go, and then just tapers off. It's probably very unlikely that we're going to find ever somebody with 10. All right. Shortcut formulas. Because everybody likes a shortcut, right? Alright, so here is the shortcut method of finding the mean and variance of a binomial distributions. Okay? And we can verify with tables We'll show a table, but using the preceding example of debit card purchases, to find the mean, mu, we take n times pi. So basically, 10 times 0.28 will equal our mean of 2.8. To find the variance, we take n times pi times 1 minus pi. So 10 times 0.28 times 1 minus 0.28 comes out to 2.016. And again, the standard deviation would just be the square root of that number. So we already have tables constructed of this. If we want to use a table, we'll see if the homework will actually have access to the table. I know your book is probably going to have them too. But say that if the Southwest 5% of all cell phone calls all dropped, what is the probability that only 6 randomly selected calls, none was dropped, exactly 1, exactly 2, so forth and so on? See the table below. Well, if n equals 6, okay, all we have to do is find that percentage. So 5% in decimal point is 0.05. So here in the chart shows us already all of our probabilities for a binomial probability test. That'd be great. At least we hope we have all these charts. If not, well, we gotta calculate it out. Whew. Alright, cumulative binomial probabilities. Alright, so a study of Illinois Department of Transportation concluded that 76.2% of front seat occupants wore seatbelts. That is, both occupants of the front seat were using their seatbelts. Suppose we decide to compare that information with current usage. We select a sample of 12 vehicles. Okay, what is the probability that the front seat occupants in exactly 7 of the 12 vehicles were wearing seatbelts? Alright, so x is going to have to equal 7. So we got our 12 combined with 7, and 12 is the number of vehicles we've studied in the sample. So the combination is 792 times 0.762 to the 7th power. Again, as our pi is our basically rate, our percentage. And then also multiply 1 minus 0.762 raised to the 12 minus 7th power. So we find out that if we want to say 7 we're wearing seatbelts, that's a 0.0902, basically about 9%. What is the exact probability that at least 7 of the 12 front seat occupants are wearing a seatbelt? So at least 7. Well, we would have to do the probability for 7, 8, 9, 10, 11, 12. Okay, so that will take a little bit of work, and we'll go all the way to 0.9562. Okay, so again, a little bit of fun as we move forward. All right, Poisson, probability distribution. This is a discrete probability distribution since it's formed by counting. It is often referred to as the law of improbable events because the probability of an event happening is very small. So again, describes the number of times some events occur during a specific interval. The interval can be time, distance, area, or volume. 2 assumptions. Again, the probability is proportional to the length of the interval. The intervals are independent. Now, it does have many applications, basically like describing distribution of errors in data entry, the number of accidents on I-75 during a 3-month period. Because why not? We need to know that because we may need to do some safety measures. There's a lot of accidents. So, to perform a Poisson distribution, the random variable is the event of time some event occurs during a defined interval. The probability of the event is proportional to the size of the interval, and the intervals do not overlap and are independent. Thus, we come out to this formula. So, the probability of x will be mu to the x power. We have that fun e. So this is a logarithmic e. So that's basically a constant of 2.71828. That's what it is. To the negative mu divided by x factorial. Okay, so number of occurrence successes. Fine. Alright. The mean of Poisson's distribution is going to be mu equals n times pi. Or times x. I think that's times x. Sorry. My bad. It is times x. So, and again, the variance of a Poisson distribution is equal to its mean. So if it's asked for variance, it's still the same thing for the mean. So example, Budget Airlines is a seasonal airline that operates flights from Myrtle Beach, South Carolina to various cities in the Northeast. Recently, Budget has been concerned about the number of lost bags. Ann Poston from the analytics department was asked to study the issue. She randomly selects a sample of 500 flights and found that the total of 20 bags were lost on the sample flights. The mean number of bags lost, mu, is found by taking 20 divided by 500. Okay, which equals to 0.04. The probability that no bags are lost is found by taking 0.404. We're looking for a 0, no bags. And then the log of e to the negative 0.04 divided by 0 factorial. It basically comes out to 0.9608. Then we can calculate also if 1 bag or more bags get lost. Well, if we've already calculated for 0 and we're looking for 1 or more, basically that is going to be just a basic subtraction from 1. Basically what we're going to find out for the other opposite. So again, you can see the probability of a bag being lost is very small. And why not? We can use a table. So, again, it can be calculated out. So, New York LA Trucking Company finds that the mean number of breakdowns on the New York to Los Angeles route is 0.3. So, from the table, we can locate the probability of no breakdowns, 0, on a particular run. Find the column 0.3, and then, of course, subtract the 2. And we're going to end up finding out that breakdowns is 0.222. Well, breakdown possible 1. But if they want to do more, we can do the subtraction, which will be like 0.2 something. So it still can be 0.222. No. Just one of those fun things. Okay. So we finally made it. We made it to the practice problems. Or again, and you know the drill, you must, to help you out, try to pause before I explain what's going on, so that you can see if you got it right before I basically speak it. You ready? Well, okay, let's go. The information below is the number of daily emergency service calls made by the number ambulance service of Waterboro, South Carolina, for the last 50 days. To explain that there was 22 days where the call were 2 emergency calls and 9 days where there's 3 emergency calls. So again, we get to have some fun. So convert the information on the number of calls to a probability distribution. Is this an example of discrete or continuous probability distribution? We already know that's going to be discrete. And then we're going to solve for the others as we go. So, let's go ahead and take the calculator, or not the calculator, let's get Excel up. Alright. So Excel is now here. Alright. So let's go ahead and start breaking it down. First off, number of calls. We had 0, 1, 2, 3, 4. Then we had the frequency of 8, 10, 22, 9, 1. So the probability of 0 calls will be 8. Actually, to make it easy, this divided by the total, 50. So 0.16. We can just drag down. And again, you gotta verify. We're going to go ahead and do an auto sum. Yeah, make sure it is 1. Okay, so that is our probability. Next, we'll go ahead and do these as we go. Insert the row. Let's go. X times the probability of X. So basically, this will equal to X times probability So basically we got 0, 0.2, 0.88, 0.54, 0.08. Then we can keep going at X minus mu, which I'm going to put X bar, or we can put mu. Mu, again, average is the sum, or mu is the sum. So this will equal X minus 1.7. There we go. And then, of course, we can square that if we need to. Well, we'll get through all the fun stuff. I just want to keep going. Alright. So, let's go this. They want to go, what is the probability that 3 or more calls are made in a day? Well, that means px equals 3. So 3. And x is going to equal 4. We're going to add these two together, which will be 0.2. Basically, 0.18 plus 0.02 is 0.2. Okay. Again, if you want to see that plus this, and that'll be the probability of 3 or more. Okay. For D, what is the mean number of emergency calls per day? Again, the mean is right here. There we go. There's that bucket. So that is our mu, so 1.7. What is the standard deviation? So standard deviation. Okay. We gotta make sure we also multiply this by x. P. X. Okay. So this one was actually missing. So here, multiply by xpx. Okay. Alright, so it's x minus mu squared times probability of x. Sorry about that. Getting that little right column, which one we use. So we're going to use the probability of x. Okay? Then we take the square root of this number. So again, formulas. Math, find square root, there we go, of this number. So our standard deviation is going to be 1.005 if we're going round, but that's our standard deviation. Woo! That was only the first problem. Remember, we still got that binomial fun stuff coming. All right. An American Society of Investors survey found 30% of individual investors have used a discount broker. In a random sample of 9 individuals, what is the probability? All right. So, again, we're going to have this combo. Basically, again, we're using these fun numbers. So n combo r are x, pi x, 1 minus pi n minus r. So I'm going to show you how this works in the calculator. Alright, so exactly 2 of the sample individuals have used a discount broker. Okay, so we want to find out 2. Alright, so we need to get our calculator out. So here's our calculator. Fun, fun, fun. And to do the combo, we're going to have to take however many we have, which is 9, minus the number that we're looking for, 2, and we're going to have to factorial this again and multiply it by the factorial of what number we're looking for. So 2 factorial. Okay? This number right here is our denominator, because we're going to take however many people there are. So let's go ahead and copy this. Take 9, that's how many people, factorial, and divide it by our 10,000, our denominator. So it comes out to 36. Okay, that's our combo. Alright, now this is going to get multiplied by our rate, our probability. I always like to use rate, but basically this is our pi. 3 to the 2, how many we're looking for. And finally, we take this, multiply our rate, our pi, the percentage basically, 1 minus 3, and that's going to get raised to 9 minus 2. So we're looking at 0.2668. That exactly 2 will happen. Now we're going to do the same thing for 4 and 0. Okay? So 4, same thing that we got going on. We have 9 factorial. It's going to get divided by 9 minus 4 factorial multiplied by how many we're looking for? 4 factorial. Okay, this is why having a scientific calculator or any calculator with this factorial, that exclamation point, is going to help you out. If you don't have the calculator, get the calculator, please. It's going to work for you. Get a stats calculator. Okay? So, we're at 126. Okay? I like to do that separate. So, times, again, our 0.3 raised to the 4th power now. Multiply. We already know this. This is 0.7. Is the 1 minus pi. This one gets raised to, again, the total number in the sample. 9 minus what we're looking for, which is 4. So it's going to get raised to the 5th power. So it's going to be 0.17153. Or if we're rounding for just 0.1715. Again, not trying to be overly complicated. It's just a long formula. So what happens if it's 0? Okay, so again, 9 factorial because that's our total. It's going to get divided by, basically, since it's 0, it's going to be divided by 9 factorial times 0 factorial, because it's 9 minus 0 in our formula, which is still 9. Okay. Then you hit enter. So it's 1 times our percentage. So we found 30%. To the 0 power. So if we look at 0, multiply by 0.7 raised to the 9th power, because 9 minus 0 again is 9. So if we want to say none of them have used the discount broker, that percentage is 0.0403, or about 4%. Probably will not have it. That's our probability. Again, long formula, but once you start getting it down, like I said, write it down how to do a combination. It becomes a lot easier. It's just practice. Lots and lots of fancy practice. Alright. Question 5. Did I go the wrong way? I went the wrong way. I'm going to do question 5 again. So question 21. In a recent study, 90% of the homes in the United States were found to have large screen TVs. In a sample of 9 homes, what is the probability that all 9 have large screen TVs? Okay. Less than 5 have large screen TVs. More than 5 have large screen TVs. And at least 7 homes have large screen TVs. Alright. Let's go look at something. Alright, so we're going to go look at your book. So let's go pop that up. So here's your book. Now, you do need to go to your ebook. In order to get to your ebook, you'll find it on the left side. When you go to your book, go to Table of Contents and find Appendix B, Tables, and then Binomial Property Distribution. Notice we also got Poisson's distribution also right here. This can help. So we're going to look for n equals 9. There's the n equals 9. And 90%. So if we're going to look for all 9, so taking 90%, going to 9, our answer is going to be 0.387. Okay. Let me see if I can make this a little bit bigger. So again, you're going to have to find n equals 9, probability table. So this is Appendix B, B.1. And we can find, if all 9, 0.387. Nice. So if we want to find less than 5. So here's 5, but we're looking at less than 5, not equal. We only get 0.001 because the rest are 0. So that will be our answer for B. More than 5 have large screen TVs. Okay? More than 5. So, in order to do that one, we know we have 0.001 plus for 5. That equals to a total of 0.008. So more than that, you can take 1 minus 0.008 equals 0.992. Or you could just add all the ones that are above 0.5. So 0.045 plus 0.172 plus 0.387 plus 0.387 comes out roughly to the same, little rounding. So it works. At least 7 homes have large screen TVs. Okay, so we want to know at least 7. So at least, yeah. So basically that again is taking 0.001 plus 0.007 plus 0.045. Okay, so that's up to 6. 0.053. 1 minus 0.053. 0.947. So again, when they're going at least or more than, we need to total up. Again, the number that will get to it, and 1 minus that would work. Okay? That's really all they're doing. It almost sounds like they're doing more than there. But at least having it is going to be, yeah, at least 7 homes. Yeah, I think they may have had a boo-boo there. But, there we go. That one looked a lot easier using a table than anything else. Last question. Ms. Bergens is a loan officer at Coast Bank and Trust. From her years of experience, she estimates that the probability is 0.025 that an applicant will not be able to repay his or her installment loan. Last month, she made 40 loans. What is the probability that 3 loans will be defaulted? What is the probability that at least 3 loans will be defaulted? Okay, fun. So that is Poseidon's. Yeah, that's Poseidon's. Oh. So, let's see. Maybe there was a Poseidon's one. Doesn't seem like Poseidon's. Alright, just a sec.